All right, so we're going to do the Unit 4 free response solution video. And as obnoxious as Unit 3 was, Unit 4 is easy. And if you've looked this up, you know that Unit 4 is all about momentum and impulse, and collisions and stuff. So here's the question right here. It says, of course, read the question carefully. All the parts may not have equal weight. And then they present you with this graph. And the graph is a graph of force versus time. Okay, and now if you get this in the AP test and you don't know that it's a Unit 4 question, this is going to be your first clue, because the graph of force versus time leads you to impulse. And they have a bunch of dots here, and these are roughly in a line going from 3 up to about 6 over the course of 12 seconds here. So the narrative says the students are running an experiment to determine the mass of a block without using a scale. The students set up a block on a horizontal surface of negligible friction. That's important. They then attach a force sensor to the block that is at rest. That is important. The sensor is then used to exert a force on the block, moving it along a straight line. The force exerted as a function of time is shown in the graph above. At a time of 12 seconds, the block is moving at 1.5 meters per second. Okay, so we're going to exert this force. This force seems to increase as we go, and we are going to... all right, sorry about that. So we got an increasing amount of force, and it's going to cause this block to accelerate from rest up to 1.5 meters per second. So question A, explain how the students could use the graph to estimate the impulse exerted on the block. All right, we're going to explain about impulse, okay? And so what we're going to do here is we're going to get our Unit 4 free response question, part A. We are going to be explaining, well, impulse is equal to the integral of the force over the time. It also is equal to a change in momentum, but more importantly, it's the area under a F versus T graph. And I think that's the thing that you need to say. You might want to say that you, because the force is changing, you might want to say something that you have to either find a shape or find an average velocity. And we'll see what happens when we go to do this next bit here, because that's next. II is calculate the estimated impulse exerted on the block for the time interval 0 to 12 seconds. Okay, so that was I. Now we're going to have II, and we're going to actually calculate it. Now, I see this thing as being kind of a straight line going here, and you could say we need the area of this trapezoid, which is the area of this rectangle here, plus the area of this triangle here. Or you could simply say we're going to take this line of force and we're going to say the average between 3 and 6 is about 4.5, and we're going to treat it as if it was this average velocity the whole time. Either way that you do it, you're going to get the correct answer. Let's go ahead and do this. I'm going to say that the average velocity times the time is going to be the impulse. And the average velocity is 4.5 newtons. So 4.5 newtons times 12 seconds gives us a grand total of 54 Newton seconds, or 54 kilogram meter per second, either way. There we go. Okay, so that's oh, I changed to red. What a crazy man. That's section II under A. So now part B says calculate the mass of the block. Okay, now there is no additional part of the question on the second page, so part B is simply calculate the mass of the block. Let's go ahead and do that. How are we going to find the mass of the block? Well, they did kind of lead you into this. They did tell you that the impulse, which by the way is J on the formula sheet, is 54 Newton seconds, and that's going to be equal to the change in momentum, which is equal to the mass of the block times the change in velocity, which is equal to the mass of the block times the final velocity. So I guess mass is going to be impulse, that's J here, divided by final velocity, 54 divided by 1.5. And that gives us a mass of 36 kilograms. First of all, that's not very reasonable for a lab experiment. That's a pretty big weight to be pushing around in the lab with a force sensor. I think they didn't quite nail this one, but whatever. We'll give them a break on that. Okay, so now we're going to move on to part C, and as you saw, there was some sort of narrative before part C. When the time equals 12 seconds, the force sensor loses contact with the block, which continues to move along the horizontal surface. So the losing contact means no more force. And continues to move along the horizontal surface. When the time is 20 seconds, the block encounters a rough area, okay, now we have friction, and comes to rest in 25 centimeters. On the graph below, sketch a graph of the speed of the block as a function of time. Okay, so we do know that between 12 and 20 seconds, we're going to have a constant velocity. The force sensor is no longer touching it. That means there's no more acceleration. And we do know that when we get to the rough patch, that this thing is going to skid to a stop, comes to rest. So it's going to skid to a stop, and that's under the action of a constant force. So the speed will be a constant slope. But the force that was accelerating the block is not constant. It started small and got larger. So we need a slope that starts small and gets larger. So we need a curving section here, flat section here, and a straight section here that goes back down to a speed of 0. And so this would be the answer to part C. For the reasons that I recommended, this is a non-constant force. This is 0 force. And this is a constant force. So that's why these things have their shape. All right, we're hauling butt. Let's go. Now, D, calculate the coefficient of kinetic friction between the block and the rough surface. Okay, so calculate the coefficient of kinetic friction. That's part D. Let's remember that we have something that is going to be a rough surface, and then it is going to, in a distance of 25 centimeters, oops, 0.25 meters, it is going to come to rest. Let's see now. It's going to come to rest. So the V final for that will be 0. V initial for that will be 1.5 meters per second. We also know that this thing has a mass of 36 kilograms. How are we going to do this? Because we have a distance. This really needs to go back to the work energy theorem. So let's just say the work done by friction is going to be equal to the change in kinetic energy. That is to say that the work done by friction is the integral. No, we don't need an integral because it's I don't think we need an integral, but it's going to be a simple integral. It's the integral of the force over the distance, and that's going to equal 1/2 mass times velocity initial squared. That's how much the kinetic energy changes by the total amount of initial kinetic energy. Okay, what is this force? Well, the force is friction, so this is going to be the integral of mu mg. And this is why I said it's a very simple integral, because there's no x in here. And that's going to equal 1/2 mvi squared. Okay, so the integral becomes just x. And so, so mu, the m's cancel. Oh yeah, mu equals, and then we're going to have 2gx on the bottom, and on the top is going to be vi squared by the time we're done here. So we need 1.5 squared divided by 2 times 10 times 0.25. Okay, 1.5 squared is 2.25. 10 times 0.25 is 2.5, and 2 times 2.5 is 5, so there we go. We got an answer of 0.45. No units because it's a coefficient of friction. Yeah, we're cooking with gas now. We are really flying through this stuff. Now, part E, for which I will need a new fresh sheet of paper. Part E says the students repeat the experiment. Don't they always? The students repeat the experiment with a block that has twice the mass of the original block. The students exert the same average force on the block. The students again get the block to move with a speed of 1.5. Please respond on a separate paper with directions from your teacher. Which of the following gives the best estimate for the time range when the new block reaches a speed of 1.5? And we have choices of 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20, or greater than 20, and justify your answer. So let's have a look at what we did here, and let's see what happens with the mass of the block. Okay, so the mass of the block is easiest to get at if we look at acceleration. So because so many things have changed, I don't think we can look at what we did before. So let's look at part EI by itself. The time has changed. The mass of the block has changed. The final velocity hasn't changed, and the force has not changed. So the force is actually going to lead us to an acceleration, and the acceleration is going to tell us how long this takes. So what is the force? The force is an average force of 4.5 newtons. And this is going to act on an object. It's going to act on an object that is twice as massive. So that means 4.5 newtons acting on something that's not 36, but 72 kilograms. And so that's going to give us an acceleration of, and I'm doing this numerically. I think you might have been able to do this symbolically, but I'm just thinking numerically right now. This is an acceleration of 0.0625. Okay, and now that acceleration of 0.0625 is going to have to get us up to a speed of 1.5. So I think I'm going to use this equation. And I can do this because I know I don't have a constant acceleration, but I'm treating as if it's constant in this sense. So 1.5 equals 0 plus 0.0625 times t. So it looks like 1.5 divided by 0.0625 is going to give me my time. 1.5 divided by 0.0625 is going to give me a time of 24 seconds. Hey, that makes a little bit of sense. It took 12 seconds to get a mass 1 thing going up to 1.5, and with the same force, a double mass thing is going to take twice the time. So we're going to have to answer that the time greater than 20 seconds is the appropriate answer. Now, in part II, and look at me, I'm totally spread out all over the place here. Let's get this going. In part II, assuming the new block reaches the rough surface with a speed of 1. Oh, justify your answer. Well, I did all the work, so I did justify my answer. Assuming the new block reaches the rough surface with a speed of 1.5, is the distance it moves in coming to rest greater than, less than, or equal to the distance the first block moved on the rough surface, and justify your answer. So now I guess we can look at, no, did we do any work here? We did work in D. Is any of this going to change according to the mass? No, the mass canceled out from the kinetic energy and the normal force part of this thing. So we could say that same, and that's because mass canceled. Okay, this is the solution other than the graph part that we did here, and I've looked at the points that they assigned to it, and this particular one, part A, there's 1 point for mentioning that the area on the curve is the impulse. Part AII, there is 2 points for calculating the area under the trapezoid and getting a numerical answer. Part B, the impulse momentum calculation is worth 2 points, 1 for using impulse momentum, 1 for the actual numerical calculation. Part C was worth 4 points. 1 point for a concave upward section curving in the first third, 1 point for a horizontal line in the middle third, and 1 point for a straight descending line in the last third, and 1 extra point for the fact that this needs to be continuous and it ends on the x-axis. They're really stretching to give you some points in that section. Part D, using energy or work to solve this problem, and then 1 point for the numerical substitution. Part EI was worth 3 points. 1 point for choosing the time greater than 20. 1 point for some sort of relationship between the force and the time, and a point just for mentioning that the time goes up. Then part EII was only worth 1 point, the justification that the mass cancels out. So there we go. That's today's lesson, and I hope you did well on this particular one. I'll get the last solution video up during spring break or shortly thereafter.